We've set up the pipeline and passed buffers to the shader. Now we'll pass images to the shader in the form of textures. Textures allow us to paint our geometry with images. They use a UV coordinate system that starts in the top left with 0, 0 and ends in the bottom right with 1, 1. We'll also use depth textures here, which keep track of the depth of each pixel drawn to the screen and use this information to sort objects from front to back. Without this, we can end up with objects in the background drawing over the top of objects in front of them. To draw a texture, we'll once again use a bind group to pass the data to the shader. The process of creating a texture to attach to that bind group is pretty similar to creating a uniform or a storage buffer. We'll create a structure to hold the bind group and bind group layout, and we'll create a couple functions that will initialize the structure. The first will be a function that creates our texture data structure from a byte array and the image dimensions. We'll also create a function that creates the structure from an image file, but it just reads the file into an image buffer and passes the data into the first function. Our fromBytes function will create the texture using the device createTexture function. It requires a set of texture usage flags that are really similar, sometimes the same, as the buffer usage flags from before. We'll also need to create an extent3D structure that defines the dimensions of the texture. We'll only be working with 2D textures and MIP level counts of 1 here. We're populating this texture with data, so we need the texel copy texture info structure, which is a view that acts as a handle for us to copy the image data to the texture. We'll also need the dimensions of the data we're writing in the form of a texel copy buffer layout. Using these, we can write the image to the texture. Next, we need the actual bindings of the texture, which take the form of a texture view and a texture sampler. The texture view allows us to access the image data as a variable in the shader, and the texture sampler gives instructions for how the texture should be mapped to a surface. The sampler tells the program how it should handle mapping the image to a geometry that doesn't match its size. Should it tile the image? Should it blur a stretched image to make it smoother, or use a nearest neighbor filter to keep the pixels intact? Things like that. We'll set up our bind group layout to have a texture binding type and a sampler binding type. Both will be visible to the fragment shader. We'll then create the bind group itself and pass our 2 variables to it. We need to create some geometry to actually bind this to, so we'll create a rectangle made of 2 triangles that we can stretch the image across. The vertices will have a 3D vertex position and a 2D UV coordinate field, so we'll need to update our buffer layout to match. We'll use this example object to create and store the texture data structure using the function we created from before. Lastly, we'll need to add the bind group layout to our pipeline layout bind group layouts array and make sure the texture bind group gets set in the render pass. That's the CPU side code. So now we'll look at the shader. This one is pretty simple. The vertex shader directly passes the vertex position and UV coordinates to the next stage, and the fragment shader will use the input UV coordinates along with the texture bindings we set up to sample a color from our image and send it to the frame buffer using the texture sample function. We can update this texture by using the queue_writeTexture function again. We'll create a function that passes in the new data and its dimensions and create the same texel copy buffer layout, texel copy texture info, and extent3D structures we did when creating the texture. We'll also need to keep a reference of the WGPU texture object we made in our original function so that we can use it to create the texture info structure. The dimensions of the data can be the same size or smaller than the texture, but any bigger will attempt to write outside the array memory and throw an error. This function doesn't do a bounds check to stop that. We'll go to the update function from our uniform buffer project and create some data from our frame buffer. This is just a rectangle that's half the size of the screen in each dimension that will give us a simple way to show that the texture is updating. I made a rectangle that shifts from black to white, but it was boring, so I made checkered black and purple squares instead. We can also render directly to a texture by passing a texture view to the render pass color attachments view. We'll demonstrate this by first having the shader draw an image from a texture. We'll target a new texture directly with the render pass, then save a copy of the result to our original image texture. The window size is smaller than the texture size, so the image will be scaled to the window dimensions and only copy over the corner of the image texture. This means that we're effectively scaling the original texture and copying it into the corner of itself. We'll repeat this each frame, which recursively scales the image into the corner. We'll also render the texture to the window each frame, which will show us the result. We'll create a new function that will create a render target texture. All we actually want is to create a texture that has the render attachment flag. We don't actually need a bind group since we aren't passing this to the shader, and we probably don't need to initialize the data since we're going to write over it anyway. But we'll just repurpose the fromBytes function so we don't have to reconfigure our structure for this case. We'll just add a flag that allows us to add the render attachment during texture creation. Then we'll write a createRenderTargetTexture function, which will pass our new isRenderTarget parameter to the function and hand it some dummy data. The last thing that we'll do is give the texture data structure a reference to texture view since it already creates this and saves us from creating it before each render. We'll need two textures now. The render target, which we'll save in the app structure to prevent some borrow checker issues, and a copy texture that we'll pass to the shader. We'll repurpose the texture from previous examples as our copy buffer, so most of the code is the same. We will need to manually swap the RGBA to BGRA to match the render format, and we'll also need to pass the render texture into the render function, and then point the render pass to the render texture view. We'll run the render pass as normal, but we'll need to run the encoder copy texture to texture function. This requires us to create a texel copy texture info structure for both the target and the destination textures, as well as an extent 3D for the texture size. We'll keep the defaults and pass the WGPU texture object to the texture info structures, and the copy size will use the width and height of the screen. Passing these all into the copy function should be our last step. Lastly, we'll talk about the depth texture. The depth texture contains the depth information of the screen. The render pass can use this information to sort objects by depth in order to prevent overlap and objects in the background being drawn over the top of objects toward the screen. We'll need to fill out the depth stencil sections of the render pipeline structure and the render pass structure. Most of this is left as the default, but we'll need to attach our depth texture view to the render pass depth stencil section. Our texture will also be a render target since the render pass is writing the depth information to it, so we'll need to add the appropriate usage flag when creating it. That's all it takes to add depth comparison. We can see the result if we copy the texture to a buffer and save it to an image like we did for the storage buffer. The process is similar, but we'll need to use the texture and a copy buffer to create texel copy texture info and texel copy buffer info structures, which will pass into the encoder copy texture to buffer function. The buffer info structure requires a layout that, for this operation, requires a bytes per row that is divisible by 256, so we'll need to add in some padding when we create the buffer. Aside from keeping in mind the padding, mapping the copy buffer and saving it to an image is the same as the storage buffer example we did in the previous video. The depth format is a float32, so we'll convert the expected value of 0 to 1 stored as float32 to a gray color with an 8-bit color depth, where each color channel ranges from 0 to 255. You probably won't see much since we're using a flat rectangle, but we can shift the Z position of one side of the rectangle to test out the buffer. We should see a gradient pattern. This will probably be the last WGPU video I do for a while. Hopefully this acts as a jumping off point. I wanted to give general overviews, but it quickly devolved into code tutorials, which are pretty tedious to make, and I'm not sure how many people are interested anyway. I wanted to give it a shot since the graphics tutorials I've seen still left me with questions, but I'm not quite sure that I did any better. If you're interested in the topic, there are resources in the description and on the GitHub. I'd like to come back to graphics and shaders eventually, but for now I want to move on to some other projects that will hopefully happen soon. If you like these videos and both want to and have the means to support me, I have a Patreon in the description. Thank you so much for watching, and I hope these have been helpful or at least interesting.